Good afternoon, everyone. I hope you're all settled with our food and ready to hear the talk. So today's speaker is Vishwadeep Dey. He's a friend and a colleague, and he works at the Intelligent Source Systems Lab under the supervision of Professor Krishnaprasad. And he works, he's a PhD candidate. He's soon going to defend his thesis on the synthesis, analysis, and reconstruction of pursuit and collective motion. He did his bachelor's in Jadavpur University in India, and after completing his bachelor's, he went on to do his master's in systems and control in Indian Institute of Technology, Bombay, and did his thesis with Professor Ravi Banavar before he moved to University of Maryland to pursue his PhD. And I'm sure this talk is going to be interesting. Hope you enjoy it. So let's welcome Vishwa.
Thanks, Vishwa. Yeah. Good afternoon, and thanks for coming to this talk, even just the day before Thanksgiving. So the last couple of decades have witnessed a tremendous advancement in unmanned vehicular technologies. For example, these quadcopters and underwater sea gliders are quite common in application domain, and these vehicles are being applied in many areas. For example, surveillance, search and rescue mission, environmental monitoring. In particular, these sea gliders were deployed in Monterey Bay back in 2004 for a month-long experiment to study underwater ocean corridors. And recently, bio-inspired robotics is gaining importance, and there is a group at Michigan State University who have developed this robotic fish, and currently this robotic fish is being deployed in the Great Lakes to locate and stop fish of interest in that region. And here at ISR, a group of Professor S.A. Gupta is doing research on these bird-inspired robots called Raven, and probably many of you have watched YouTube videos on this Raven, and it's quite amazing. But the way these vehicles are deployed in the field, for example, drone deployment or underwater search missions, involves a human in the loop in terms of piloting these vehicles. And that gives rise to an Achilles heel in the system in terms of the vulnerability of the communication link between the command station and the vehicle. At best, the link can be lost. At worst, the link can be taken over by an adversary. So this gives rise to the need to develop complete autonomy for this group of unmanned vehicles. So on the other hand, we can notice collective motion in a number of natural settings. For example, ant mills or fish schools to bird flocks in the sky. There are many more examples in nature where you can see a large number of agents are interacting with each other and giving rise to some coordinate motion pattern. So today I'm going to tell a story about how we can use these inspirations from nature and develop algorithms for collective motion in a group of robotic agents. And this is what I'm planning to cover today. I begin with a brief description about the models that we'll use in the talk, and the main part of the talk will have two sub-components. In the first part of this talk, we'll describe our findings from analysis of biological pursuit and collective motion. So here we'll use custom-made algorithms to extract parameters of motion, namely speed, curvatures, etc., from observed position data, and then we'll analyze those parameters to get an insight about the underlying flight strategies and control laws. Because that's our main focus. Once we have an idea about the underlying flight strategies and control laws, then we can apply those principles to robotic agents. So the second part of the talk will discuss about two particular strategies inspired by our findings from this analysis, and will show how they can guarantee some desired behavior. And we'll conclude the talk by showing some implementation results. Okay. So before going into the details of analysis and synthesis of collective motion, we begin by describing a model which we'll use throughout the talk to describe an agent's motion. So here we represent the position of an agent along the trajectory by this vector r. Now, if we assume that the velocity of the agent never goes to 0, then we can say that we can easily define an unit tangent vector along the trajectory. So the first equation here describes the velocity in terms of a speed, in terms of speed nu and normalized velocity vector x. Now, once we have a unit vector x, we can pick two more vectors y and z in such a way that x, y, z forms an orthonormal triad or a reference frame. Now, these three equations describes the evolution of that frame along the trajectory. So these parameters u and phi represents the natural curvatures for the system. So these natural curvatures are very well related with classical curvature or the inverse of turning radius. So if you take the square root of the sum of this u and phi, you will get the classical curvature. Okay. So that's the model that we'll be using throughout this talk, and this particular model is called natural frame equations. So first we'll talk about our findings from the analysis of bat pursuit events. So the echolocating behavior of bat, or the property of bat that it uses sonar waves to detect and localize its targets or its environment, was first studied back in early 1917 or so, and the study was inspired by the need arise during the First World War, because people were looking for proper ways to use sonar waves for detecting submarines and so, and that was the starting point for studying bat echolocation. So people have been studying the echolocating behavior of bat for a long time, but until recently, a very little research was done in understanding the pursuit strategies and feedback mechanism in bat echolocation. And one of the major stumbling block in that direction was the unavailability of proper high-speed motion capture system. So fairly recently, Ghosh and Prof. Moss, they studied echolocating bat behavior and have shown that when a particular bat tries to pursue a moving target, they use constant absolute target direction, a particular type of strategy, to chase the target. But in a later study by Chen Qiu, they have shown that when the setting is changed from a single bat and single target to two bats competing for a same target, they switch the strategy. But in both the studies, they have used some qualitative measure to do the analysis. So in this present work, what we have done, we performed a comparative analysis of the flight strategies in these two contexts and have shown quantitatively that there is a switch in underlying flight strategy. And our analysis also reveals some estimate of the behavioral latency involved in this pursuit behavior. Okay. So now, before going into the details of this analysis, I'll just introduce the candidate flight strategies that we'll be considering for our purpose. So classical pursuit is one of the oldest form of pursuit strategies which has been studied. So in classical pursuit, here it involves two agents, a pursuer and an evader. So here the red trajectory corresponds to that of the evader, and the blue one corresponds to the pursuer trajectory. So in classical pursuit, the pursuer moves in such a way that its velocity is always directed towards the evader position. So you can see that this gray lines corresponds to the line joining the pursuer position with the evader position, and you can see that the pursuer is moving in such a way that its velocity is always directed towards these lines, right? And in motion camouflage or constant absolute target direction flight strategies, the pursuer moves in such a way that the baseline vector moves in parallel. So in the context of bat motion, this strategy is known as constant absolute target direction. But normally in the context of visually insect flights, people call it motion camouflage, because normally most of the insects, the visual insects have compound eyes, and the way they perceive depth is not through stereo reconstruction. Normally for human beings, we perceive depth through stereo reconstruction, but in visual insects, they have compound eyes, so they use optic flow to get an idea about the depth or the distance of an object from the eye. So optic flow is basically the transverse component of the relative motion of the target. So in motion camouflage, what happens is because the pursuer moves in such a way that at the evaders' eye, the pursuer have a constant position with respect to some point in infinity. So for example, if the evader is looking at the pursuer with respect to sun angle, the pursuer always appears to be stationary. So that's why they call it motion camouflage. But it might be a bit of misnomer in the context of backlight because there is no thing known as acoustic flow. It's kind of not well defined in that context. So these are the two strategies that we'll be using in our analysis, and these are candidates. So now we introduce the contrast function to measure these strategies in a quantitative way. So in this case, R represents the relative position of the pursuer with respect to the evader. So the contrast function lambda is used to measure classical pursuit. And if lambda is -1, then that will imply classical pursuit has been achieved. So, okay, what is lambda? It's basically the direction cosine between the pursuer's velocity and the relative position of the pursuer with respect to evader. And lambda equals -1 implies that those two the velocity and the baseline should be aligned. On the other hand, motion camouflage is quantized by the contrast function gamma. So in this case, R dot is basically the relative velocity of the pursuer with respect to evader. And when we have gamma equals -1, we can say that the motion camouflage or CATD has been achieved. So now we introduce two particular properties which will be instrumental in understanding an individual's role in a dyadic interaction. So we introduce two notions, namely following and converging. So we will say a particular flight segment following if the pursuer's velocity is directing towards the evader. So in the sense that basically it says that the pursuer's velocity has a negative projection on the baseline vector. And we'll call a flight segment converging if the distance between the ends is shrinking. So with these two notions, we can say that flight can be categorized into 4 classes. Namely, class 1, when the flight segment is both converging and following. Class 2, when the flight segment is only following. Class 3, when the flight segment is only converging. And class 4, when the flight segment is neither following nor converging. And why we need this tool? Because we'll be studying the interaction of 2 bats. So remember, in this case, we have 2 different incidents. In one incident, a particular bat is trying to catch a moving target. And in another instance, there are 2 bats which are competing for a single stationary food source. So when there are 2 bats and a single stationary food source, the setup appears to be symmetric. So in that interaction, we need to know which one is playing the role of a leader and which one is playing the role of a follower, right? And that's why you need this tool. So now when we focus, okay, and please interrupt me if you think that you need some more explanation about something. So in the bat-bat interaction, we can see that the bat 1 pursues bat 2 for around 66% of the time, while if we reverse the role of bat 1 and bat 2, it follows bat 2 for only around 27% of the time. So from this analysis, it becomes clear that in a bat-bat interaction, although the setup was kind of symmetric, there is a strong asymmetry in an individual's role. And we call a particular bat, in this case bat 2, the follower in this interaction. And if we look at the bat-insect interaction, we can easily see that the bat pursues the moving target or the moving insect for around 74% of the time. So there is a clear evidence in favor of following behavior. So now we'll go into the strategy analysis. And the way we perform strategy analysis is by looking at the distribution of those contrast function values. So here, this figure shows the distribution of contrast function values for classical pursuit. And this histogram shows the distribution of contrast function values for motion camouflage or CATD. So basically, now if we recall what we mentioned in 2 slides back, that the particular contrast function, if it is very close to -1, can be considered as a strong evidence in favor of that particular strategy, right? So here you can notice that for classical pursuit, the contrast function values are very much around the -1 value or desired. So we can say qualitatively that, or quantitatively that there is strong evidence in favor of classical pursuit. And if we look at the percentage of time when the contrast function value was less than -0.9, we can notice that here the value was less than -0.9 for around 32% of. Yeah.
How did you get the values?
So basically, once we had the observed positions, we can extract velocities, right? From
what position of what? Like what kind of experiments did you use to find out this value?
So okay, so the experimentation part it involved like letting the bats fly in a dark room, and motion capture systems was used to observe the position of the bat. In this case, there are 2 bats. So motion capture system was used to record the positions of individual bats, and that gave us the trajectory. And we looked at the trajectory and used our algorithms to extract velocity, curvature from that data, and we used our previous formula to compute these contrast functions. Does that answer?
How did you make sure, like, define which one is classical pursuit and which one is what?
Yeah, so in this case, this one, you can see this lambda values are the distribution of the contrast function values for classical pursuit. And this is the distribution of contrast function values for the motion camouflage. And as we can see that in this case, for most part of the flight, the contrast function value was close to -1, which is a strong evidence in favor of CP. So basically from these 2 figures, we can conclude that there is a strong evidence in favor of classical pursuit in comparison to motion camouflage, right? Excuse me. So now this demarcation between the evidence in favor of this particular strategies becomes more evident if we focus our region of interest to class 1, or when both the flights were converging and following. So in this case, we can notice that the classical the lambda values goes below -0.9 for around 42% of the time, while it goes below while the gamma values or the contrast function values for MC or CATD goes below -0.9 for around 7% of the time. So it basically reconfirms our findings that there is a strong evidence in favor of classical pursuit when 2 bats are competing for a single food source. Now, we go to the other instance. When a single bat is trying to pursue a moving target. In this case, we can notice that there is a strong evidence in favor of motion camouflage comparison to CP. So here, the lambda values goes below -0.9 for around 9% of the time, while the gamma values goes below -0.9 for around 32% of the time. But although in this case we have some evidence in favor of motion camouflage, but the strength of evidence is not as good as what we observed in our previous example, right? And even if we focus only onto the class 1 flight segments, or the flight segment which is both following and converging, we can see that there is stronger evidence in favor of motion camouflage, but still the strength of evidence is not quite convincing. As we compared to what we noticed in the previous case. And that leads us to the analysis at next level. So far, we're looking at the evidence at the level of flight strategies. So now, what follows, we'll look at the evidence at the level of feedback mechanism, namely the steering control laws. So the way we perform the steering control law analysis is by comparing the empirically observed curvature values, namely empirical values of u and v, with the curvature values predicted by theoretically plausible control laws. Okay, and this, so basically previously some of our lab members have shown these particular control laws can ensure convergence to CP or NC. And in this case, as we are dealing with biological elements, it's reasonable to expect some behavioral latency. And that's why I have incorporated delay into this cost mismatch minimization problem. And it can easily be shown that this mismatch minimization problem can be approximated by a correlation maximization problem. Any questions? So this correlation maximization problem reduces the computational complexity by a great extent. So now here we are looking at the comparison between empirically observed curvature values and the curvature values predicted by the theoretical feedback laws. And we can, the second row shows the correlation plots. So here I'm plotting correlation as a function of delay. So we can see that in this case we are getting strong evidence in favor of classical pursuit. And the behavioral latency is around 170 milliseconds, which is comparable to the behavioral or sensory motor delays observed in mammalians. Now, if we go to bat-insect interaction, we can see that here we have a very strong evidence in favor of MC or CATD. And the behavioral latency is around the order of 120 milliseconds. So basically, and we can easily see that the strength of demarcation is much more evident in the context of bat-insect interaction than that observed in bat-bat interaction. So now we can say that to get an idea about the underlying feedback mechanism or the interaction between the agents, we need to look at the levels of both flight behavior and the feedback mechanism. If we look only at one level, the conclusion might not be proper. That's a very important point in this analysis. So basically through this analysis we have shown that there is a context-dependent switch in flight strategy in bat foraging, right? So now we'll go into the second part of the talk. So now we'll shift gear and move to collective motion in its true sense, because so far we are considering pursuit behavior, which involve two agents. So here we'll show some results from our ongoing work with Starling data. So here we are collaborating with Andrea Cavagna from University of Rome, and they have collected data near a city center at Rome. And here we are going to analyze three particular flight events. So these flight data were collected from a rooftop using multiple camera networks, and they used stereo reconstruction to extract individual trajectories from a set of two-dimensional images. So here these three particular events. So the first event involves a single turn, while the second one involves two consecutive turns in opposite direction, and the last event is a minimally maneuvering flock. So here we have used algorithms to extract speed and curvatures for individual trajectories. And then when we're looking at the correlation between an individual's curvature with the curvature of its neighbor as a function of delay, we can notice that the correlation between an individual's curvature and the curvature of its neighbor depends both on the number of nearest neighbor and the delay. So that gives an idea about what to look for. It implies that we need to look for the effect of both neighborhood size and the behavioral latency. behavioral latency is quite expected because we are dealing with biological elements. So now we consider individual starting. And excuse me. So now we are considering an individual starling along with its neighborhood. So given an individual starling and a neighborhood, we can easily define the velocity of its neighborhood center of mass. And if that neighborhood center of mass velocity is not equal to 0, then we can easily look at the direction cosine between an individual's velocity and the velocity of its neighborhood center of mass. Now, if that's called the coherence, and if I average that quantity over the whole flock, that is known as the flock averaged coherence. So what I'm showing here is the variation in the flock averaged coherence as a function of the neighborhood size. And we can see that the flock averaged coherence gets maximized by considering around 5 to 7 nearest neighbor. So this results actually goes in line with another finding where they have used more complicated analysis to show the importance of 5 to 7 nearest neighbor. And currently we are looking into the underlying what can be a possible steering control laws for this kind of behavior. And we have, in what follows, we'll show that particular steering control law, which we have gained insight about from this study, can guarantee convergence to a particular behavior. So this is a very much ongoing work. So now I'll go into the synthesis part. So here I'll discuss a particular flight strategy named as topological velocity alignment, which has been inspired by our findings from the Starling data analysis. So in topological velocity alignment, we consider an individual agent I from a group of n agents along with its neighborhood n script ni. So now, given an agent I and its neighborhood ni, we can define the neighborhood center of mass velocity in this way, right? And if this velocity is not equal to 0, then we can easily define the unit tangent vector along that velocity, and it's denoted by xni. So in topological velocity alignment, the agents try to move in such a way that the direction cosine between an agent's velocity xi and x sub ni, the direction along the neighborhood center of mass velocity, is 1. So they are trying to move in the same direction. So quantitatively, we can use this contrast function to characterize this velocity alignment strategy. So we can easily notice that these contrast function values can vary from 0 to 2. Right? And in this case, this contrast function values theta I equal to 0 implies that the velocity of the ith agent is aligned with the velocity of its neighborhood center of mass. Right? So, I forgot to mention that in this case we are using the self-steering particles model that I introduced at the beginning as the model for evolution of trajectory. Right? So now we can constrain this particular feedback law. Basically, so these are the natural curvatures of the ith agent, and they are governed by the measurement in terms of the neighborhood center of mass velocity. Right? So we'll show that using these particular steering control laws, we can make the agents move parallel to its neighborhood center of mass velocity. So here we are considering a planar system along with the velocity vectors x1 and x2. The two agents' position are denoted by the vector r1 and r2. So now the corresponding state space of the system can be thought of as the two copies of Euclidean group of planar motion. So basically, corresponding to each agent, we need to keep track of its position and its orientation. So the position and orientation of an agent in a plane can be represented as an element of this special Euclidean group of planar motion. And as we have two agents, we need two copies of that space to represent the state of the system. But as we are interested in relative position and orientation of the agents, we can consider the space of shape variables, which can be characterized by three parameters. Because the relative position will have two components, and the relative orientation can be represented by one angle, right? So alternatively, we can use two angle quantities, namely psi and phi, and then distance rho as three scalar shape variables. And then we can show that the dynamics of these scalar shape variables can be represented in this form. And in this case, we have used the feedback laws. We have used this particular feedback law restricted to planar setting. So now we can show that the dynamics of phi is self-contained and stable. Now what is phi? Phi is just the mismatch in alignment. So we can easily show that if basically under this dynamics, the mismatch goes to 0. So if I define a subspace of this shape space as the set of configurations where phi equal to 0, that particular subspace is closed under these dynamics. Moreover, it's attractive. Wherever you start in this space, it will be driven to this subspace, right? Do you have any question, Deepak? So there is a proof for asymptotic convergence. And finally, I'll show some results which came out of this collaboration with Kevin Galway, the faculty at Naval Academy in Annapolis. So he has started cyclic pursuit, which is basically a setting where there are n agents and agent I pursues agent I plus 1. So basically there's a cyclic interaction among the agents. And in that setting, you can use classical pursuit or motion camouflage or different kind of strategies as a building block. Or even TVA can be used as a building block in that setting. So here we are considering constant pairing pursuit, which is a generalized version of classical pursuit as a building block. So previously he has shown that under that kind of interaction and with constant pairing pursuit as a building block, some interesting behavior emerges, namely rectilinear equilibrium or circling equilibrium. But where the circling equilibrium emerges in terms and the radius of the circling equilibrium are determined by the initial position and orientation of the agents. So it was not very effective from a design perspective. So here we have introduced a beacon in a network of cyclically interacting n agents and have shown that some interesting behavior emerges. So in this case, we are considering n agents and each agent's position, namely the agent i's position is denoted by the symbol Ri, and its velocity is denoted by the symbol Xi, and Rb represents the position of the beacon. And we have basically all these agents are moving in a planar setting. So there is only one control, namely the U, right? And that control can be expressed in terms of this feedback law. Okay, so there are too many symbols here. So basically what I have done, similar to the previous analysis, I have used scalar shape variables to parameterize the space. Namely, I have used the symbols rho I to denote the distance between agent I and I plus 1, and I have used this angle kappa I and theta I to represent the angle between the heading of an individual agent and the baselines. And I have used the symbol rho IB to represent the distance between agent I and the beacon. And here we can see that the feedback law has two components. So the first component is coming from the original feedback law if there were no beacon. And the second component is a beacon dependent term. So and we can show that a stable equilibrium exists in terms of, for any positive lambda, we can show that a stable equilibrium exists, and the radius of the circling equilibrium and the angular separation of the agents on the circle are completely determined by the choice of these parameters alpha I and alpha IB. And another feature of this control law is that it doesn't require any explicit measurement of distance. So although it seems that the feedback law involves rho I, or the distance between an agent and its neighbor I plus 1, the whole component, the whole term can be thought of as an optic flow element. And then with proper sensors, you can measure this quantity without knowing the distance explicitly. So now I will conclude this talk by showing some implementation results. So here in our lab, we have developed a test bed where we can implement these control strategies in a group of mobile robots or field robots. So we have a couple of these pioneer free robots, which are differential drive robots. Differential drive means that each wheel can rotate independently, and that allows us to have zero turning radius for these robots. And we have this motion capture system which can sense the position of these robots. And then we use a computer running robot operating system, or ROS, to compute the feedback control laws. And we close the loop by using a dedicated Ethernet communication between the motion capture system and the control computer, and Wi-Fi from the control computer to the robot. So now you can ask, like, so far I was talking about decentralized control, or control without any need for communication link between a common station and the vehicles. But here what we are doing, because to design robots which has all the computing and sensing capabilities on board, it is another volume altogether. So here we are just offshoring the measurement and control and computing requirements to a separate motion capture system and a separate computer. But the control, we have to keep in mind that the control laws are truly decentralized in nature. So now I will show some implementation video. So here we have implemented the topological velocity alignments on a group of mobile robots. And so this particular video clip has 3 small sub-videos, and the first video will show that by using that particular strategies and by making each individual to interact with 3 of its nearest neighbor, we can make the robots move in a single direction. We can notice that although they started initially going to different direction, after some time they go to the same direction. And here, where this is the plot of the contrast function theta, and it goes to 0 quite fast. So now we can show that if I reduce the number of neighbor, or if there is a reduction in the neighborhood size, that can give rise to split in the flock. And it's quite interesting because normally in the context of Starling flock, so you can notice that in presence of a predatory threat, the group of Starlings split into smaller subgroups. And here we're trying to emulate that kind of behavior. So we have a group of 6 robots, and at this moment they are interacting with one of its nearest neighbor. And you can see that as there is a disturbance, and it's trying to make this robot to go in other direction, you can see that finally there are 2 groups of robots. So basically, one of the robots encounters an obstacle, and that forces it to move in other direction. And as the neighborhood size is small, it gives rise to 2 subgroups in the flock. So now I will show another video where we have implemented the cyclic pursuit. And here we are using our cyclic beacon referenced cyclic pursuit control for 5 agents, and we can see that eventually they all end up doing a cyclic pattern around this beacon. And by choosing the design parameters properly, we can select, like for given a radius, we can easily choose the parameters in such a way that they will circling that particular radius. So now we will just move the beacon from one position to another, and we'll show that the whole group moves from one position in the lab to other position, and the new radius is quite stable. So they will be circling the same radius. So we can notice that there is small oscillations in the distance from the beacon to the robots, and that can be attributed to the fact that in our modeling we always considered the agents to be point particles, but in reality the robots have some physical dimension which is not negligible. Like they have a width of around 300 millimeter, and the magnitude of this oscillation is around 100 millimeter. So that's much less than the physical dimension of the robot. And if we look at the behavior observed compared to the theoretical predictions, we can see that there is small error here at steady state, but this error is much less than the physical dimension of the robot. And this error can be attributed to the fact that in our model we thought about the agents to be point particles, but in reality they have some dimension. And also we have noticed another factor behind these oscillations is that we always assume the lab floor to be perfectly horizontal at the same level, but there's a small slope in the lab floor. And as we are looking at the XY component of the position, that gives rise to some oscillation. So basically, if we draw a circle on a plane, and if you are looking at it not vertically but with a slight angle, it will look like an ellipse, right? So similar kind of thing is happening here. So that was all what I wanted to tell today, and thanks for your attention.